Hey everyone, welcome back to the channel. Today, I'm diving into one of my favorite topics, detecting bacterial flagellar motors in tomograms using deep learning. You know those tiny propellers bacteria use to swim? They're powered by molecular motors that are so small, you need specialized microscopy just to see them. Automatically finding these motors is crucial for research, but it's like looking for a needle in a microscopic haystack. I'm excited to walk you through an awesome notebook by Mehdi Sharifi from the BYU Flagellar Motor Detection Competition. We're going to explore how deep learning, with YOLOv8 at the helm, tackles this challenge in biomedical imaging. Whether you're into computer vision, biomedical applications, or just curious about how AI solves real-world problems, you're in the right place. Let's kick things off by talking about setting up the environment. The notebook starts off by extracting and installing the Ultralytics package so we can use YOLOv8. I really appreciate how it imports a wide range of libraries right from the get-go, from visualization tools like Plotly and Seaborn to deep learning frameworks like PyTorch. It even sets random seeds for reproducibility, which is key in making sure you get the same results every time you run the code. Plus, it checks for GPU availability and sets up the device accordingly. Those little details really add up when you're working on a competitive project like this. Once the environment is set, we move on to exploring the data. The notebook begins by loading the training labels from a CSV file, and you can see that there are 737 entries to work with. It turns out that most tomograms have very few motors, with an average of just about 1.13 per tomogram, and sometimes as many as 10. This imbalance in the data is important to note because if the model only learns to predict no motor, it might still score well overall. That means we have to be thoughtful about our evaluation metrics, focusing on things like precision and recall. Digging a bit deeper into the data, you see that there are 648 unique tomograms among those 737 entries, with some tomograms appearing more than once. The notebook reveals that 286 tomograms have no motors, 313 have one, and only a few have two or more. When there are no motors, the motor axis coordinates are set to -1, which is a neat little indicator for those cases. There aren't any missing values, so the preprocessing is a bit smoother. The dimensions of the tomograms are also really interesting. The z-axis, representing the number of slices, ranges from 300 to 800, while the x and y dimensions can be as large as 1912 by 1847 pixels. That's a lot of high-resolution data, and it really underscores the complexity of what we're working with. You also see the voxel spacing clustering around values like 13.1, 15.6, 16.8, and 19.7. This likely reflects different scanning settings, which might affect how the model detects motors at different scales. The notebook then takes you through some descriptive statistics and visualizations. You get to see histograms that show a peak near -1 for the motor coordinates, indicating no motor, and a long tail of positive values when motors are present. It's also fascinating to look at the array shape features and the voxel spacing distribution. These visual insights really help in understanding what you're dealing with before jumping into model training. I also love the part where the notebook displays actual tomogram slices. These grayscale images, although noisy and low in contrast, are a great reminder of the challenges in electron microscopy. The flagellar motors show up as small, darker regions, and you can see how variable the data is. Each slice tells its own story, which is why robust preprocessing and data augmentation become so important. Next, the notebook dives into preprocessing for YOLOv8. Now, let's talk about YOLO in detail. YOLO stands for You Only Look Once, and it's a family of real-time object detection models. Instead of painstakingly scanning through an image multiple times, YOLO models are designed to quickly look at the entire image just once to identify objects and their locations. In our case, the object we want to detect is the bacterial flagellar motor. To get our data ready for YOLOv8, we need to transform it into a format that YOLO understands. Here, it extracts 2D slices from the 3D tomograms around the motor's position. Imagine taking thin slices from our 3D tomogram, like slices of bread from a loaf. For each slice, we want to enhance the contrast so the motors are more visible, and this is done by normalizing them using percentile-based contrast enhancement. Crucially, we also need to tell YOLO where the motors are in these slices. This is done through bounding box annotations. For each motor, we create a box around it in the 2D slice and provide these box coordinates to YOLO. This notebook generates these bounding box annotations in the YOLO format. The data is then split into training and validation sets based on the tomogram, ensuring there's no overlap. This split is important so we can evaluate how well our model generalizes to new, unseen data. By the end of this stage, you have over 4,000 slices, with around 3,200 for training and 800 for validation, each annotated with the motor's precise location within a bounding box. With the data prepped in YOLO format, it's time to train the YOLOv8 model. We're using a pre-trained YOLOv8 model, which means it has already learned to detect general features from a massive dataset of images. This pre-training helps our model learn faster and better on our specific task because it doesn't have to start from scratch. The notebook loads these pre-trained weights. To prevent overfitting, where the model learns the training data too well and performs poorly on new data, we use early stopping. This technique monitors the model's performance on the validation set and stops training automatically when the performance starts to degrade. We also set up periodic checkpoints to save progress, so we can always go back to a previous good model if needed. Training runs for up to 30 epochs, but early stopping kicks in around the 15th epoch because the model has already reached its peak performance. During training, YOLOv8 learns to adjust its internal parameters to accurately predict the location of flagellar motors within the bounding boxes. On the validation set, the best model hits a mean average precision at an IOU threshold of 0.5 of about 0.836, a pretty impressive feat for such a challenging dataset. Mean average precision, MAP, is a common metric for evaluating object detection models, and a score of 0.836 indicates good performance. After training, the notebook shifts focus to making predictions and generating submissions. Now that we have a trained YOLOv8 model, we can use it to detect motors in new tomogram slices from the test dataset. The inference process, which is the process of making predictions, is highly optimized, utilizing GPU enhancements like half-precision inference and dynamic batch sizing to speed things up. Half-precision inference means using a less precise numerical format to perform calculations, which can significantly reduce computation time and memory usage on GPUs. Dynamic batch sizing automatically adjusts the number of images processed at once to maximize GPU utilization. A really clever technique used here is 3D non-maximum suppression, or NMS. Since we are detecting motors in 2D slices of a 3D volume, we might get multiple detections for the same motor across different slices. 3D NMS helps to combine these detections across slices into a single, more accurate 3D detection. The final submission is generated as a CSV file that contains the predicted motor coordinates for each tomogram, all in under a minute for the sample data. Wrapping it all up, this notebook is a stellar example of how deep learning techniques, typically used for everyday object detection, can be adapted to solve complex scientific problems. It takes you through the entire process, from data exploration and visualization to preprocessing, model training, and generating predictions, in a way that's both accessible and technically sound. I hope you found this walkthrough as exciting as I did. If you're tackling similar challenges in biomedical imaging or just love exploring the intersection of AI and science, I'd love to hear your thoughts. Don't forget to like, subscribe, and drop your questions or suggestions for future videos in the comments below. Thanks for watching, and I can't wait to see you in the next one. Happy learning and keep building.